Hello, 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 hello. Oops. Hello. Okay. Good afternoon, everyone. Let's get started. Okay. So I noticed that several students came to ask me about homework one problem. About the problem three, I think came to ask me during the class or after class, before the class or during the office hour. So some of you are confused about whether the orders matter or not. As I replied directly, the orders matter because in the homework we said, if you take a look carefully, there's one sentence saying we do it sample without replacement, right? That basically means you're gonna pick up the ball for twice, right? You got two balls, that means pick up a ball for twice. Of course, the first time you pick ball one and then ball two, it's different from your first time you pick ball two and ball one. Okay, does that sound good? Right? If you're still, if any of other, you're still confused about this, I would like to clarify again in the class. Hopefully you're not bothered by this problem again. But other than that, the problem is, we believe is straightforward. And again, I mean, if you haven't started or haven't finished the homework one yet, I would suggest to start quickly because I believe the due is tonight, right? So please spend some allocate a dedicated amount of time, maybe 30 minutes. It should be sufficient for all you to finish it. Okay. Another thing I want to clarify is about quiz. So quiz is open doesn't mean like you have the time until like say Friday midnight. It's not that long. So every time we pop out quiz, we just made announcement saying, okay, this quiz will take about 10 minutes or 15 minutes. So remember, every time you open the quiz, it will show you the time limit. So don't open it and just leave it alone. And after that, I mean, after the time passed, it will pop up the correct answer. So given that, we cannot like give you some makeup exam because you know the answer. So just be aware that there is a time limit for the quiz. It's not like, okay, once it's available and it will be, you can take it anytime like and spend like as long as you want until say Friday midnight. It's not like that. So you can pick up any time you feel comfortable, you feel confident, you can concentrate to open the quiz and finish quickly. It won't take you much time. Okay, any question regarding the homework and quiz schedule? Okay, perfect. So let's first quickly review what we have discussed in the last lecture. So in the last lecture, we actually talk about a very important rule. It's called a base rule. Oh, sorry, I should come here, right? So what is base rule? So sometimes it is also called inversion lemma of Bayes inversion lemma. So why is it called inversion lemma? It just tells you the relationship between two conditional probabilities. The two conditional probabilities are inverted in terms of conditional part and unconditional part. Right? For example, if I want to look at what's the relationship between the conditional probability of B given A and the conditional probability of A given B. You see, this is kind of reversed, right? And you switch the order of A and B. Then there's a way to calculate their relationship. I mean, quantitatively, right? So if you want to compute probability of B conditional on A, you just multiply the conditional probability of A given B by P of B divided by P of A. So it's kind of like you're going to multiply a ratio between the two marginal probabilities. Then you can invert the conditional probability. Right? That's the basic rule. And as we emphasized, right, this is a really, really useful and really, really widely used rule. So we hope everyone will keep it in mind, right? As to how we arrive at this rule, it is just based on our definition about the conditional probability, right? So we're not gonna go through this detail again, but the basic idea is that, okay, I'm according to the definition of the conditional probability, I can write down the joint probability of two events, A and B, right? Namely, the probability of the intersection between A and B can be written as the marginal probability of B times the conditional probability of A given B. But symmetrically, you can also write it down as the marginal probability of A times the conditional probability of B given A. Right? According to the definition of the conditional probability, they are the same. Both decompositions, you see, this is one decomposition, this is another decomposition, lead to the same joint probability. And then, of course, these two decompositions are equal to each other. Then you directly arrive at this Bayes rule. Okay. So this is, please practice this and to help you strengthen the understanding of Bayes rule, right? So we use several examples to illustrate how we leverage Bayes rule to compute the conditional probability, right? So so one interesting problem during our discussion is a so-called brain teaser, the Monte Carlo problem, right? So basically, you're on game show. You got three doors, right? You got three doors, and you know that, and also all audience knows that there will be one car. There will be a car behind one gate, and behind the remaining gates are goats, right? So you have freedom to choose whichever gate you want to open, right? So we're assuming the contester, right? Some contester, some participant of this game, right? Random pick up gate one, right? But he hasn't opened the gate, right? Then the host, who knows exactly where the car is behind, then opens gate three and shows you a goat. Then the question, there will be a choice, right? You can choose to stay with your initial choice to open gate one, or you're gonna change your choice to open gate two. You got a question? No. I'm just repeating this problem setting. Okay, so then the question we're interested in is that, okay, shall we switch to open gate two, or we just stay with gate one? Yeah, we know that we should switch, right? The reason is that using some Bayes rule, we can show that now, given the host open gate three and show you the goat, the probability that the car is behind gate two is 2/3, is twice as much than the probability the car is behind gate one, which is 1/3. Right? That's a very good way to practice Bayes rule, right? But here, we want to review this problem because we want to refresh our mind and to let everyone to be on load, right, about base rule, right? But here, I want to illustrate this in another way, like small, like brain teaser problem, solving a brain teaser problem, right? So here's our insight, right? Okay, so know that initially, when we have 3 doors, right? You know, the car has the equal chance to appear behind any gate, right? So that means if you pick gate 1, you have 1/3 chance to see the car behind gate 1, right? But you're gonna have a 2/3 chance that the car behind either gate 2 or gate 3, right? So this is gate 2, this is gate 3. So now the host opens one gate, right? And show you this is actually not a car, it's a goat. So that means the chance of 2/3 of the car behind gate 2 and 3 now all collapsed into gate 2, right? Because you know that, okay, gate 3 definitely will not have the car, right? And from our prior belief, we know, okay, the chance that car is behind the doors, the gates 2 and 3 is 2/3, right? But now you know, definitely behind gate 3, no car, just the goat. Then this total chance 2/3 is collapsed onto gate 2 only, right? But if you stick to gate 1, your chance that you're gonna see a car behind gate 1 won't change, it's still 1/3. That's why we would rather switch to gate 2, because the opening gate action from the host actually moves the probability or move the chance from gate 3 to move to gate 2. So your gate 2 has better chance to win. That's how people explain this to, general audience or general people, to ordinary people, how we should solve this problem. That's why it's called brain teaser, right? But if you want to more rigorously address this problem, right? More rigorous proof why this probability 2/3 is all collapsed onto gate 2. You have to calculate, right? You have to really calculate, given the host opened gate 3 and revealing a goat, what's the probability your gate 2 hides a car? Or what's the probability your gate 1 hides a car, right? Right? Actually, our practice in the last 10 minutes or 15 minutes about this is just to show this. Okay. Okay, so we're not gonna do this again, but just quickly review the process, right? So if you want to show this with base rule, we're gonna define a few events, right? We define event A1 as the car is behind gate 1, event A2 as the car is behind gate 2, event A3 as the car is behind gate 3, right? So know that A1 intersection with union with A2 union with A3 must be the whole sample space, right? And also those events are pairwise disjoint, meaning that A1 intersection with A2 is empty, A1 intersection with A3 is empty, A2 or intersection with A3 is empty, right? Because these two events cannot happen simultaneously, right? You cannot have a curve is both behind gate 1, gate 2, right? That's impossible event, right? And then we define a fourth event C as the host opens gate 3 and which reveals a gate, a goat, right? Then what do we do? If we really want to evaluate whether it is beneficial for us to switch from gate 1 to gate 2, right? We would like to calculate what's the conditional probability of A1 given C, and what's the conditional probability of A2 given C, right? So that is, what is the conditional probability that the car is behind gate 1 given C? That is, the host opens the gate 3, right? And what is the conditional probability of A2? That is the car behind gate 2, condition that the host has opened gate 3, revealing a goat, right? So you just need to compare these two conditional probabilities and decide which one give you better chance to win. You make a choice, right? And then the calculation of this two probability exactly follows the Bayes rule, right? So I mean, I'm just writing down a formula, right? I'm not gonna repeat the calculation. So it's basically, you're gonna use the Bayes rule, which means that this conditional probability can be written as the conditional probability of C given A1. You see, this is reverse version, right? Times the marginal probability A1 over the marginal probability of C, right? And this guy is the same, right? The reverse conditional probability P of C given A2 times P of A2 and divided P of C, right? So the K is how do you correctly figure out these two conditional probabilities, P of C given A1 and P of C given A2, right? There's a subtle difference here, right? It's actually different, right? So I'm not gonna repeat this. I'm not, but I had to suggest you, like, if you feel kind of like forgot our discussion or feel unclear about this, please spend some time reviewing our lecture and derive something. That is will very helpful for you to understand Bayes rule. So why Bayes rule is useful? So in practice, what we often know is that given some given some causal effect, what is the consequence? Say, if your car has transmitter problem, then your car might just stop in the road, right? You know this, and this represents a forward probability, which is one type of conditional probability, right? So it's causal, right? You already have this, and the more knowledge you know about the system, the machines, the spacecraft you built, right? The more clear you know those forward conditional probabilities, right? Say, given your electricity system doesn't work, what's the probability your, I don't know, I'm just saying randomly, what's the probability you're gonna crash, or you're gonna stop running, or your lights will be off, whatever, right? You know, and given that your water supply is shut off, right? And what's the possibility that you cannot take any shower after Wednesday, something like that, right? So you know those knowledge, but in the practical situation, is often you need to infer reversely. Like you say, your car suddenly is stored on the road. It just doesn't start. Or you just switch gear to driving mode, it doesn't work, right? You need to infer what is underlying cause. Basically, that mathematically is to calculate the reversed conditional probability. That is, you see some consequence, right? You see some bad things happen. What is the potential causes, right? Maybe it is because your transmitter has problem. Maybe your battery is dead. Maybe your sensor failed, right? And you need to diagnose this, right? And when you do this kind of inference, you're going to rely base rule. And it's also kind of like the foundation for many expert system, right? Maybe you haven't heard expert system for you guys or for this for young people at this time. But when I was a undergrad student, expert system is still hot work. It represents some kind of early revolutionary progress in artificial intelligence. Basically, you build up like a domain expert and use rules or based in inference, given some kind of like observation or measurement, you're gonna diagnose things. Some kind of expert system was even used to diagnose diseases, right? And it was very popular before. That is how those expert system was divided at that time. Right now, like expert system are everywhere. It just has already, on everything. You just notice. You just don't know. For example, in your refrigerator, in your car, in airplanes, aircrafts, almost all the bigger system, right? It has already been matured, but the underlying mechanism is based on the space rule. The system, there's some monitor system like Zero is some kind of computer. They want to collect the data and they want to infer what's happening if there's something, some parts are malfunctioning. Okay, any question regarding base rule? Okay, so actually we'll talk about that problem in the last lecture. So the probability of C, you directly calculate this guy is not very explicit, right? So what we want to do is I want to leverage the so-called total probability rule, right? So you can consider your sample space has been partitioned by these three events, A1, A2, A3, right? So you can decompose as P of A1 times P of C given A1, right? Plus P of A2 times P of C given A2 plus P of A3 times P of C given A3. Do we agree? Right? Then the question is that you need to figure out every term in this decomposition, right? So we know PA1, PA2, PA3 are all 1/3 equal chance, right? And this guy is easy to compute. This guy easy to compute. There's just one thing just to be careful. What is the P of C given A3, right? What is this probability? Y is 0. Yes, exactly, right? That's the case, right? You know, okay, given A3, the C cannot happen, right? That's the impossible even. So the probability must be 0. So that means this guy will be simply 0. And you just add this guy and this guy. This will give you, I forgot number, but you can calculate. And eventually, you'll see this guy will be P of A1 given C will be 1/3, and this guy will be 2/3. Okay. Another question? Okay, great. So next, we're gonna introduce a very important concept called random variables, right? So actually, if you want to dive into a little bit more in depth in probability theory or statistics, you have to know what's the definition of random variables. So when I was an undergrad student, it took me a while to really understand what does it mean for random variables. Perhaps there's no a very rigorous definition in my textbook, right? So, but intuition is like this. Intuition is like, okay, let us associate some like the outcomes of random events or random experiments to some numbers. And no, because the outcomes of your random experiments has randomness naturally, right? Like you toss a coin, you flip a coin, you see heads or you see tails, right? Those are associated with probabilities. Then the numbers which are associated with outcomes will have probability as well. So when we say, okay, the probability of random variables take something, that's where the uncertainty or the randomness comes from. And in the future, it will be natural for us to say things like, okay, the probability this random variable less than 3 will be 1/4, or the probability of this random variable between 3 and 5 will be 20%. That actually not talking about the number itself. It's talking about the underlying associate outcomes of the random experiments. And the random variable is like a bridge. Right? It's like a connector. Connects those all kinds of like random experiments results to some numbers in the real number space. How to make a connection? So here we give the definition of random variable. So random variable is a function. So don't get confused by the literal name. Random variable is not variable. It's just a function. A function from the sample space to real numbers. So basically it is mapping, right? Function is mapping. It maps from the element in a sample space to a real number in a real space. Right? So when we say a sample space, it must corresponds to some kind of random experiment, right? So you toss a coin, your sample space might be just heads and tail, right? And if you look at, if you toss a coin for twice, right, your sample space will be all pairwise combinations of heads, tails, right? So actually, this sample space can be flexible, can be sample space from arbitrary random experiments, right? And then for any element in this sample space, means any possible outcome of the experiment, we'll find a number to represent that. That's what a random variable does. Okay, so here let's use several concrete examples to show the definition, right? So let's see, we roll a dice twice, right? I mean, you just throw the die, right? You just roll a die and you see some point, right? And you roll a die again, you see some point, right? So through this twice rolling of the dice, you got a sample space, right? Those sample space are just pairs of all possible combinations of points, right? So if we can write it more explicitly, you can consider like, okay, my first rolling of dice will give 1. The second is also give 1, right? That's one possible outcome of my experiment, right? Or the first point is 1 and second 2, or first is 1, second 3rd, first 1, second 5, 4, first 1, second 5, first 1, second 6, right? But it's not finished yet, right? We also have the possibility, right? A new outcome could be the first point you say after rolling die is 2, right? But the second point is 1, right? 2, 2, you name it, right? Until 2, 6, right? And or your first rolling, you get 3 points, and the second get 1. First get 3 points, second get 2. Da da da. First got 3 points, and second got 6 points, right? So you can just enumerate all possible pairs, right? Until that first got 6 and second 1, first got 6 and second 2, until both rolling got 6, right? So how many possible outcomes do we have for this sample space? How many? 36, right? Because in each rolling, right, you have 6 possible points, right? And you roll it twice, right? So it's 6 times 6, which is 36, right? Okay. So we can define a random variable. You see the random variable, which maps this sample space, including 36 outcomes, to a real number. One such mapping would be, I just add up the 2 points from the 2 rolling experiments, right? From the rolling results, right? So that construct our example of the random variable. It's just I plus j, right? Does it make sense? I can define another random variable, which is just I minus j. I can also do this, or I times j. Question? It doesn't matter. So you can define your random variable. We'll talk about that later. Like, for example, for the same random variable value, you probably will have multiple outcomes in the sample space correspond to the same value, right? That is perfect normal. That's fine, right? But we'll talk about that in a minute. But any question regarding the definition of random variable? Okay, again, we want to emphasize random variable is a function. It's not a variable, right? It is a mapping, right? It maps any element in the sample space to a number. This map is almost arbitrary, but there's some subtlety here. We're not going to discuss about details, especially when we talk about the sample space is infinite, uncountable. If you're random variable, if you define a random variable value, random variable must be measurable. That's about measurable function. Otherwise, you won't have a consistent definition of probability function. There will be some paradox, but this is not scope of our class. Just to give you, we don't need to know the random variable essentially is a mapping. I want to map the various weird outcomes from all kinds of random experiments to some numbers. Okay, so, and why do we introduce random variables? In other words, why do those mathematicians invent this concept called random variables to torture you guys and torture me like 10 years ago? Right? Actually, there is some important motivation. So first, although we define like probability function, right? We define sets, it's very natural. And it seems like applied to every possible random experiments and random phenomenon we're interested in, right? It's still not very convenient in that, because whenever you want to summarize some patterns or rules or properties out of these experiments, right? You have to look into the particular random experiments. You have to look into, okay, I'm doing gambling, or I'm doing like a hedge funding, or I'm trying to make a decision whether I'm gonna send my rockets to the sky, right? This is very, very domain specific. And the natural question will be, can we define a tool such that I can unify all kinds of like random experiments, outcomes into one space? I can study their common properties or common patterns or common rules. And through the random variables, things will become much more convenient. Why? Because we mapped whatever outcomes, right? It could be heads up, tails up when you roll when you toss corn. It could be the points when you roll die, or it could be the temperature tomorrow. It could be the stock price, right? You all map them into the real number space. Then we just need to look into those mapped numbers in the real space and use the purely abstractive and math languages to study them. That's why people define random variables, right? You can get rid of like a specific context of the random experiments. You just look into the numbers in the real space, and you study what kind of properties, what kind of common patterns, what common rules can we extract from those numbers. And also, interestingly, if you look into those random experiments, their outcomes in a real space, right? And you abstract them into the real space through random variables, and they may reveal some very, very interesting feature, which is very hard to discover in the original view, in the original experiment. That's why, like mathematicians introduce random variables and then define a bunch of like concepts on top of that. And we'll see later, like expectation, like variance, like probability density functions and cumulative density functions, all kinds of stuff, right? And actually, modern probability theory is built upon this. Okay, any questions so far? Okay, so now, if we have constructed such a map, namely random variable, meaning that we map the random outcomes, the outcomes or all kind of random events or random experiments into real number space. That means we can also use the values of random variables to define events, right? So our events, the definition of our events is not just restricted to sets of the outcomes in the original context of the experiment, like you're doing gambling, you're doing you're investing stock price, you're measuring the temperature, those kind of stuff, right? You can just look at numbers, right? You can just look at random variables values, and based upon that, you can define a variety of events. Okay. Let's see, how do we define events with random variables? Right? So we introduce this notation, right? You see this big bracket, right? X equals A. So X is a random variable. Okay. So we use this bracket with X equals A to define an event. Such event contains all the elements in our sample space for which the random variables evaluates to A. In other words, it contains all the elements in the sample space after random variable mapping, we got A. Right? So formally, the definition is here. So we define the events x equals to A as all omega in the omega space, in the sample space, such that when you evaluate x over omega, it is A. So back to the question some of you asked like a few minutes ago, right? So when we talk about what if several different elements, they correspond to the same random variable value? Yeah, it is allowed. It is allowed. It actually corresponds to some kind of particular event, right? Right. And then we define the probability of this event as P of x equals to A, right? This is like perhaps many of you have seen in the textbook before, right? When we say any textbook, statistics book, you always say, okay, I got a random variable. I want to look at what is probability x equals to A, what is probability x equals to 3, something like this, right? So they're talking about the specific event associated or defined based on the random variables. Any questions so far? Okay, let's just use some concrete example to make sure everyone feel comfortable about this definition, right? Okay, so going back to our sum of dice example, right? Suppose we roll the die twice, right? Our random variable is defined as the summation of the 2 points of the you say after you roll the die twice, right? So now let's see what is the corresponding event. What is actual event for s equals to 5? So we mentioned that before, right? So we got a sample space like this, right? You roll the die twice, right? You want to look at. Sorry, maybe I should. Oops, well, that's too small. Let me just paste here, right? Your sample space consists of all pairs of points possible. You roll the die twice, you see, right? So now, according to the definition, an event defined in this way is all possible elements in the sample space such that our random variable, sorry, S ij equals to 5, right? So now, which elements satisfy this? Can we name it? Exactly, right? We just look at which pairs in a sample space will give the summation to 5, right? So we just take a look, right? We just exhaustively enumerate. So first point is 1, then the second point must be 4, right? Because their summation is 5. And then first point is 2. How about second point? 3, right? We're looking all pairs in the sample space whose summation equals to 5, right? And the first point is 3. The second is 2, right? And the first point is 4. Second point is 1, right? So you see, out of all 36 possible elements in the sample space, you will have 4 elements. When you evaluate with this random variable s, it is equals to 5. So that those elements form the event that s equals to 5. Okay. So what's the probability of s equals to 5? Yes, right? Remember, it's just the equal chance roll throw in, right? So you got 5 outcomes, possible outcomes in your event, and your sample space has 36 outcomes, right? So the chance that your event is just 5 over 36. Any question? Oh, sorry, it's 4 over 36. It's not 5 over 36. This typo. It's just this is your question? Uh-huh. Yeah, s equals to 5 represent events here. Remember, event is a set, right? It contains all the elements in the sample space. When we evaluate with s, it is 5. It's actually 4 elements. Okay. Other question? Okay, great. So let's take a rest for 5 minutes and we continue. Okay. Hello. Hi, everyone. Let us continue. So we have show some example. How do we map our definition of the event based on random variables to the event we are used to, right? So let us keep impressing ourselves, right? Keep strengthening our own understanding. Let's say another event, right? S equals to 7. So we define another event based on the random variable s equals to 7. So now we want to write down what is specific set of the elements in the sample space which correspond to this event. And can anyone show me how to write down those elements? Yes, exactly, right? So again, look at the definition, right? So when we define an event like this, it just means we're going to collect all the elements in the sample space such that when we evaluate the random variable at those elements, it equals to A, right? So for here, because we know that Sij, this random variable, which is simply I plus J, right? So just look at all pairs of Ij's whose summation is 7. We can do it together, right? So you can imagine the first one is 1, then the second one must be 6, right? And the first one is 2, and the second one must be 5. And first one is 3, second is 4, first is 4, second is 3, first is 5, second is 2, and first is 6, second is 1, right? So how many
找到了这个与 for the 5 check on the 2 and 46 有关的结果，请看。
Sorry, this is a very silly Siri. I don't know. It just pop up from time to time. So how many elements do we have in this event? 6, right? So now, how do we compute P of S equals to 7? Yeah, 1/6, right? That's after you reduce it. If we directly read it out, it should be, okay, 6 over 36, right? Then it can be reduced to 1 over 6. Okay. Yeah. Another example, I mean, it's just practice. We look at this 2 dice experiment, and then we define another random variable. I multiply with J. Right? So let's do this, right? So we can pick up A from a set of values, 3, 4, 12, 14. Let's see what is corresponding event, meaning the set of elements which should be included in this event, right? So first, for x equals to 3, what are the pairs inside this event? Yes, exactly, right? So 1, 2, 2, 1. Is there any other possible pair? No. Why? This guy, multiplication. Oh, yeah. You're right. Sorry. Yeah. 1, 3. and 3, 1. Okay, thank you. Thank you for pointing out. Okay, so any other possible elements which are also inside this set? No, right? Because you can't find, say, you put a point 4 in the first, there won't be any point when you multiply with 4 equals to 3, right? So that we have identified all the elements in this event, right? Okay. Let's say x equals to 4. Right? What are the possible outcomes in the event? One, 4, 4, 1, and 2, 2, right? Great. Okay. How about the event defined as x equals to 12? Mm-hmm. 1, 12, 12, 1. Yeah, that's a that's a good, right? So we just need to exclude those impossible event, right? Okay. So yeah. We first consider, like, say if I have the first point to be 1, right? Then according to the definition, then my second point must be 12, right? That's actually not possible because your die your dice at most has 6 points, right? So that's not possible. So we have to exclude it. So then we can consider like 2, right? The first point is 2, the second one is 6, right? Because 2 multiplying 6 is 12. And if the first point is 3, what's the second point? 4, right? Right. And if the first point is 4, 3 will be the second, right?
这是 Black 的内容介绍。Black 为韩国 OCN 于2017。
Okay, how about point 5? Is it possible? No, it's not possible because no point multiplying with 5 will equals to 12, right? That's not an integer, right? So, okay, the last possible candidate could be the first point is 6, and then the second is 2, right? Okay, that's what we have for x equals to 12, right? It contains 4 possible outcomes or elements from the sample space. Okay, so the last event we consider is x equals to 14. So can anyone give the possible elements in this event? Why is the empty set? Yeah, exactly right. So be careful. This actually defines a impossible event, right? Why? Because you won't find any pair in the sample space where you multiply the 2 items given 12, right? You can try, right? Or given 14, right? Like 1, 14, 2, 7, 7, 2, they're all not possible, right? So the last one, the last event actually is just a empty set. Any questions so far? Okay, so now let us try to compute this probability. So what is the probability x equals to 3? Yeah, 2 over 36, right? You got 2 elements, your set, your event, and out of 36 possible outcomes in the sample space, it is 2 over 36, 1 over 18, if you like, right? So what is Px equals to 4? Three over 36, right? 1 over 12, right? What is Px equals to 12? Four over 36, right? 1/9. So what is Px equals 14? It's 0, right? Because it's empty, right? The size of empty set is 0, right? So it's 0. Right? Okay, any questions so far? Great. So given the random variables, right, and given the definition of the probability, given the definition of events based on random variables, so next we introduce the so-called probability mass function, right? So what is probability mass function? It's just the probability of the event defined in the way as we just described. Namely, what's the probability of x equals to a? I view it as a function of a. So this is called probability mass function, right? So if we going back to this example, right, we talk about the choice of a from 3 to 4, 12, 14, right? So you can view 3 corresponds to the probability 1/18, 4 corresponds to 1/12, 12 corresponds to 1/9, and 14 corresponds to 0, right? So this gives the example of a probability mass function, right? So if x equals to some a corresponds to an impossible event, meaning it's an empty set, then this function will be 0 for a. Okay. So sometimes the probability mass function is also called a probability density function, abbreviated as PDF. So that will be very frequently saying in statistical textbook or probability textbook. You also say people are mostly interested in probability density functions and how they vary along with the input A and so on, right? So usually we can draw a probability mass function as kind of like discrete plots. How can we do that, right? It's like the y-axis represents the function value. The x-axis represents different choices of A, right? So if we take the examples here, right, we actually have knowing the values at different A's, right? 3, 4, 12, 14, right? So when we draw it, we just pick up 3 here, 4 here, maybe 12 here, maybe 14 here, right? And we know Px equals to 3 is 1/18, right? That means F3 is 1/18. Then you can draw a vertical line, represents probability, right? And this is 1/18. And F4 equals to 1/12, right? So you draw another vertical line here. This corresponds to 1/12. And F12 equals to 1/9, right? So here you're going to draw a higher vertical line. which represents the number 112. And for 14, what is at 14? 0, right? So you just place a point here, right? Of course, you should draw all possible non-zero probabilities in this figure, which is not very many. We're not gonna exhaust it, but for all the other points, because their probability mass function value is simply 0, right? So you can imagine this is just a set of like discrete vertical lines. But later, when we talk about continuous random variables, and then this function will not be that discrete. Actually, it will become some smooth function. For example, if we're talking about the Gaussian random variables at, say, at 0 mean, and you will see typically its probability mass function will look like this. It's very smooth. That means like every point in its axis, it has some non-zero probability mass function, right? We'll talk about that later. Okay. And then based upon the probability mass function, we also define this called cumulative distribution function, CDF. So what is cumulative distributive function? It is also a probability. It's just a probability for another type of events. This event is defined as in this way, like x less than or equals to a. Right? So similarly to how we define the event like x equals to a, right? So the event defined as x less than or equal to a as all the elements in a sample space such that when you evaluate x over this element, the random variable value will be less than or equal to a. Like for example, right? Let's take an example, right? Going back to maybe this example, right? So we got our random variable as ij is I plus j, right? So I want to look at the event such that s less than or equal to 4. So how do we extract the outcomes or the elements in the sample space which form this event? Any try? Any thought? Yeah, we just look at, according to the definition, right? We just look at all pairs. So we just look at all pairs in the sample space such that the evaluation of the random variable on these pairs, which is I plus j, right? Less than or equal to 4, right? That's how we define the event. So now if we look at the list of pairs which satisfy this, who will be those pairs? Any thought? It's not exhaustive, but very close, right? So as long as less than or equal to, even if it is less than, it's total fine. But let's see. You want to see? Yeah, 1, 1, right? So like, let's see, right? So if I put 1, the first point is 1, the second point is 1, right? Their summation is 2 is less than 4. It doesn't matter, right? Because it is satisfy the random variables value less than 4, right? So it is included. And similarly, you go 1, 2, right? 1 plus 2 is 3, right? Less than 4. It is satisfied. The condition is satisfied. Then you include it in your event, right? 1, 3, right? 1 plus 3 is 4. It's just equal to 4, right? It's also satisfied, so it is included. And 2, 2, right? Oh, sorry. 2 we can start with 2, 1, right? Because 2 plus 1, 3 is less than 4. It is included. And 2, 2, right? 2 plus 2 equals 4, right? Less than or equal to 4, right? And 3, 1 is also satisfying. It's also satisfy this condition, right? Their summation, the random variables value evaluated on this pair is 4, is less than or equal to 4, should be included, right? Anything else? No, right? If you start with any other point, there won't be any additional point where their summation will be less than or equal to 4, right? So this forms the event defined here as less than or equal to 4. Does it make sense? Right? So then we define the cumulative distribution function CDF as the probability of the event that x less than or equal to some specific value a, and then we'll view this value as a function of a. So this is called CDF. Okay, so let's stop here today and see you on Thursday. Yeah.
Anyway, also have a text file for the homework.
You want that?
Yeah.
Yeah, I can share with you. Yeah. That you are very welcome to use that.
Thank you.
Yeah.
I just always.
Yeah. Well, we will release the LaTeX source if you want, and you are free to include them.
Yeah. Thank you.
Yeah.
Is there like particular situations where you want to define